So, today's topic is seawater intrusion and ghyben-herzberg relation. Saltwater intrusion is the movement of saline water into freshwater aquifers, which can lead to groundwater quality degradation, including drinking water sources and other consequences, especially in the coastal areas. Saltwater intrusion can naturally occur in coastal aquifers owing to the hydraulic connection between the groundwater and the seawater. So basically the mixing up of seawater and fresh water in the aquifers in the coastal areas is called seawater intrusion or saltwater intrusion. Because saline water has a higher mineral content than fresh water, it is denser and has a higher water pressure. As a result, salt water can push inland beneath the fresh water. The higher pressure and density of salt water causes it to move into coastal aquifers in a wedge shape under the fresh water. So, due to the movement of this salt wedge, the fresh water or the water table rises, and that is why the inland becomes under the freshwater table. So in this picture you can see the movement of salt water under the fresh water in a wedge shape. This causes the rise of the water table beyond the land surface. The main reasons for the saltwater intrusion are excessive groundwater pumping from coastal freshwater wells, navigation channels or agriculture and drainage channels that may connect the freshwater and the seawater. Then the sea level rise caused by climate change and coastal floods and also oil drilling. And the major effects of seawater intrusion include scarcity of fresh water in the coastal areas for drinking, agricultural and other household consumption, and also for construction works. And the salts present in the seawater affects the foundation of structures, especially in the coastal region, the corrosion of reinforcement and the leaching of cement. So the reinforcement bars present in the foundation gets corroded due to the presence of salts. Also these salts react with some of the compounds in the cement. Thus the weakening of foundation affects the superstructure. Now, control and management of seawater intrusion. Maintain the proper balance between water being pumped from an aquifer and the amount of water recharging it. So, the excessive pumping of fresh water from an aquifer is one of the reasons for seawater intrusion. So, the water level in an aquifer should be maintained by properly recharging it. Next is constant monitoring of the salt-water interface. Restricting withdrawals from coastal aquifers and using alternative freshwater sources. Next is ponding surface water and stormwater runoff. Even we can collect the rainwater as an alternate source of fresh water. Next is using river water to recharge the groundwater. Using deep recharge wells. Then potentiometric surface mapping of an aquifer can provide important information determining the direction of groundwater flow within a confined aquifer. Basically mapping an aquifer to know the direction of groundwater flow. Using deep recharge wells, we can supply water into freshwater aquifers from an external source. Next is ghyben-herzberg relation. The first physical formulation of saltwater intrusion were made by William Baden-Gaben and Alexander Herzberg, thus called the Ghyben-Herzberg relation. They derived analytical solution to approximate the intrusion behavior, which are based on a number of assumptions that do not hold in all field cases. So this is an approximate solution and also do not work for all the cases or especially all the field cases. So today we have a number of methods to analyze the intrusion behavior, including finite element method. The ghyben-herzberg ratio states that for every meter of fresh water in an unconfined aquifer above sea level, there will be 40 meters of fresh water in the aquifer below sea level. So let's come to this sentence once again. After having a look at this equation, so the ghyben-herzberg equation is Z is equal to rho F into H divided by rho S minus rho F. And what is Z? You can see in this picture, the thickness of freshwater zone below the sea level is Z and that above the sea level is H. Thickness of freshwater zone. This is the sea level. So the thickness of freshwater zone below the sea level is Z and above the sea level it is H. So this equation relates Z and H. In this equation, rho F is the density of fresh water and rho S is the density of salt water. Fresh water has a density about 1 grams per cubic centimeter, that is 1 gram per centimeter cube at 20 degrees Celsius, whereas the seawater is about 1.025 grams per centimeter cube. So, if we substitute these rho F and rho S in our equation, Z is equal to 40H. Approximately, Z is equal to 40H. So, back to this sentence, the ghyben-herzberg ratio states that for every meter of fresh water in an unconfined aquifer above sea level, there will be 40 meters of fresh water in the aquifer below sea level. That is, if H is equal to 1 meter, Z will be equal to 40 meters. For every 1 meter of fresh water in an unconfined aquifer above sea level, there will be 40 meters of fresh water below sea level. That is, when H is equal to 1, Z will be equal to 40 meters. So, this is all about seawater intrusion and ghyben-herzberg relation. Thank you.